All right, so let's go ahead and do some antidifferentiation. Now, remember, as I said before, antidifferentiating is way more complicated than differentiating. But the good news is early on, there are some basic formulas that can really help every step of the way. So let's learn these by example or through example. So let's start with our first one. Let's antidifferentiate, or let's find the integral of 5x squared minus 2x plus 3. All right, so there are three great rules that we can use in here. Remember, a differential formula looks like, or a differential equation looks like y equals the integral of some function of x differentiated on the variable x. That's what the dx means. And so that's what I have here. But the first rule is to notice that, excuse me, the integral of f of x plus g of x, which in this case would be f of x plus g of x plus c of x, or h of x. But in this case, we're only going to show 2, but the rule does expand. Dx is the same thing as taking the integral of the f of x dx on the variable x plus the integral of g of x on the variable x. All right, so I can break apart a polynomial. That is a super helpful rule. Let's do it. I'm going to rewrite this one. I'm looking at the integral of the first term of the polynomial, 5x squared dx minus the integral 2x dx plus the integral 3 dx. Okay, so now I've broken it into smaller bites. Seems an easier way to work with it, but not necessarily something I can do. Now, first off, I can do easily. First off, I can see a constant, and I can kind of imagine that since integration is the backward or opposite or inverse of differentiation, what would I have started with to end up with a 3 if I had differentiated? And I can imagine in my mind that that this function probably started off as 3x, because to differentiate 3x leads just to 3. So this one I can kind of do in my head. This one I can do almost, I think, in my head, because it seems like, well, to get that 2 out front, I probably had an x squared. And so I can almost do this one in my head. This one is much tougher. All right, so these are just starting to think toward what would the original have had to be if I differentiate it to get whatever I'm trying to find the integral of, because what I'm doing is working back and forth again. Well, let's look at some rules, because they'll make it so much easier. Even though we can sort of imagine it, let's find some easier steps. So rule number 1, and these numbers have no significance, they're just for this lesson. And rule number 1 is just the polynomial rule in this case. Oh, and I see a mistake. Plus c. So when we integrate, we have to allow for that plus c that would have disappeared in the process. So up here, I could technically have put a plus c in here and a plus c. This was just a thought bubble, so it's not as critical. But down here, where I'm actually doing the calculus on it, I have to have the plus c. So let's get a new rule. I think I'm going to work with this last part of the polynomial and work with rule number 2, which just deals with finding the antiderivative of a constant. So if I'm looking for the antiderivative, or the integral of some constant value on a variable, then the antiderivative is just cx, which is exactly what we expected, right? C being 3, in this case 3x, plus c. All right, so let's go ahead and differentiate then this last one. So I can say that I know that this antiderivative, which means I can lose the symbol, is going to be 3x. And I'm going to go ahead and put the plus c in my formula now, just so I don't lose it. But I could wait till the end. In fact, usually you would wait till the end, but I just want to make the point, so I'm going to keep it here now. All right, then the third really helpful rule also has to do with a constant. If I'm looking for the antiderivative of some constant times some function of x on an interval x, on a variable x, then I can take the c outside, which is kind of nice. So when I'm looking for the integral or the antiderivative of some constant times a function, I can pull the constant out front and then just take the antiderivative or the integral of the function. Okay, so let's do that in both of these cases, which means I'm not going to finish the problem up in this stage, but I can definitely make it simpler to work with. So I've got a constant times a function, so I'm going to bring the 5 out front and then only look for the antiderivative of x squared on the variable x. And then here I'm going to pull the 2 out front, and then I only have to find the integral or antiderivative of x on the variable x. Okay, so that's already made my job a lot simpler, but I imagine I'm going to need 2 more rules that tell me how to deal with these. I kind of had an idea for this one, but this one I'm not really sure of, except I probably, let's go ahead and think it through just a little bit, probably I have some form of x cubed, but to bring the 3 down front to get, that would have been like 3x squared, right, to take the derivative, but I don't have a 3 in front, so there's going to have to be some sort of an adjustment that happens to this one. But I've got a great rule to work with that too. We'll just wait till we get there. So let's go to my next rule that I think would be helpful in this problem. And it tells us what to do whenever we're dealing with a variable to some power, so x to the n. In fact, that's what I'm dealing with here, where I have x to the first power, and what I'm dealing with here. So it looks like I might be able to finish this problem up in the next step with this next rule. And of course I have to put the dx in because that's super important. So remember when I showed here that we were going to have to figure out a way to adjust out in front of the x variable? Well, this is the way you do it. We are going to divide by n plus 1. Whatever the power is, we're going to divide by n plus 1. And then in the numerator, we'll have x to the n plus 1. So we're going to add 1 to whatever's in the power, which fits, right? We added 1 to 2, right? So we took 2, added 1 to 2 to get the 3 in our thought bubble. But we're going to deal with the fact that when I pull 3 out, I have a 3 when I take the derivative, but I didn't have a 3 in front to begin with. And so what do? We're just going to divide out by that value. And so when we do this, plus c, then we will have the antiderivative of a variable to a power. So let's go ahead and do that. So in this first case, I've got my 5 out front. Since I'm about to actually take the antiderivative, I can lose my symbol, and I'm left with, well, I have x squared in the numerator, or x to the 2 plus 1, so I'd have x cubed in the numerator, divided by 3, which is the n plus 1. Okay, and in a minute I'm going to show you that it actually works. And then this would have a plus c, but we're going to let this last plus c, because if this has a plus c, and this has a plus c, and this has a plus c, then all those plus c's just combine. 3 constants, 1 plus 2 plus 3, just combine to be another one big plus c. So we're not going to worry about it at this stage. Let's go to the second one, 2. And again, I'm taking the integral, so I don't have to have the symbol anymore. And I'm going to put in the denominator 1 plus 1 is 2. And so x to the 1 plus 1 is 2. Plus, bring down my 3x, and now my whole accumulated plus c. Okay, let's look and see what our final problem then, our answer looks like. 5/3 x cubed minus 2 divided by 2 is 1. So that's x squared. And look, we can see that 2 divided by 2 is 1, which means that in this case, the antiderivative is just x squared. And we were really confident here that that was a true statement when we did our thought bubble. So that actually worked out for us really well. And then, let's see, plus 3x plus c. So that is actually, I've calculated the integral. I've used the first 4 important rules that you will use over and over for calculating integrals. And let's confirm that each of these by calculating the derivative would actually have given me back this inside value, just to double check that our rules worked. So if I were to take the derivative of this first term in my polynomial, I would pull down the 3, so I'd have 5/3 times 3x squared. 3's cancel, so that equals 5x squared, and check it out, that's where I was. Let's go ahead and underline it so we can see a color and work with a different color here. Let's work with orange. So now let's work with this one. If I were to take the derivative of x squared, that would be 2x. That's exactly what I started with here. And just to complete the process, let's take the derivative of 3x. I should say, let's see, let's not put in equals in here. Let's make these little arrows because, of course, it occurs to me that they're not equal signs. I don't have enough notation to write it that way. So 3x, the derivative of 3x would lead me to 3. And that's exactly where I was here. Or I guess I could look up here at my original. And then 3 is yellow. Okay, so you can see that taking the antiderivative of a polynomial leads to a value. Antiderivative and derivative, inverse functions. So when I get the outcome or the answer or the solution to my antiderivative, if I take the derivative of the polynomial, it just takes me right back to the initial function. And that's exactly what antiderivatives and derivatives do. All right, so let's do one more example that is going to look pretty complicated, like maybe we need a new rule, but we really don't. We'll be able to calculate it just by rewriting. So example, we're going to take the integral of x to the 5th plus 3x minus 2. Not so scary yet, but as soon as I make it over x cubed, and I want to take it on the variable x, it starts to look pretty complicated. But remember, we can separate these into separate integrals. And we know from Algebra 1 that we can separate the fractions into separate fractions. So rather than look for a new rule, let's go ahead and just break it apart. So we're looking for the integral of x to the 5th over x cubed plus the integral dx plus the integral of 3x over x cubed dx minus the integral of 2 over x cubed dx. Okay, not necessarily looking better, but totally is. This first one simplifies to x squared dx, and we already know what that is. And this second one simplifies to 3x to the minus 2, right? So the x's cancel, I get an x squared in the denominator, I bring it up to the numerator, I get x to the minus 2 dx minus 2 times x to the minus 3 dx. Okay, let's take out our constants. I'm not going to worry about the first one. X squared dx plus 3 times the integral of x to the minus 2 dx minus 2 times the integral of x to the minus 3 dx. So now I can just use my rule that the integral of x to the n equals, dx, I should write, equals x to the n plus 1, divide everything by n plus 1. So let's go ahead and do that. So this one is x, 2 plus 1 is 3, divided by 3. I don't need my integral sign anymore because I've actually integrated this, plus 3 times x to the negative 2 plus 1 is x to the negative 1 over negative 1 minus 2 times x to the negative 3 plus 1 is negative 2 over negative 2. And then I'm going to take all the plus c's and pull them all together into one giant plus c at the end. Now let's simplify. This is 1/3 x cubed plus, well, -1 actually means this is going to be a minus 3 over x to the minus 1, so 3 over x, minus minus is a plus, 2 divided by 2 is 1, so all I have is x to the minus 2. Let's go ahead and put that in the denominator. Doesn't really matter, I just want to write it there for now. X 1 over x squared plus c. And that, my friends, is the integral of this ugly thing that all we had to do, I guess that could be called rule number 5 if I needed to, rewrite when you can. All right, so that is antidifferentiation formulas, part 1.